Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about characters of tori, which are the basic building blocks of torus symmetry if you want to study this symmetry in a linear context. Okay, so let's look firstly at what we mean by tori. And interestingly enough, there are various versions. Okay, so let's go through the first version. The first version is based on the circle group, and the way I want to think of the circle group S1 is just as a subgroup of the multiplicative group of the complex numbers C cross. It's just going to be all the complex numbers Z of modulus 1. Okay, so that's a subgroup of C cross. That's the one-dimensional real torus. Okay, so, it's one real dimensional. If we want to get the n-dimensional real torus here, we want to look at basically the product of this S1 with itself n times, okay? And we're thinking of this Tn as a topological group. So not just with its group structure, but also as a topological space, okay? So S1, of course, is a topological space, and so is the product with itself n times. So the two-dimensional real torus is the usual one we think of when you think of a torus, but we can talk about the n-dimensional real torus as well. Okay, so the next version that we'll look at is what's called the algebraic torus, and the data that you need for that now is an underlying field K. Okay, so we assume we have this field K. We can take it to be algebraically closed, which is quite common. And then what we do is we look at the multiplicative group K cross, and we look at n copies of that. That's the n-dimensional algebraic torus, and we're going to think of this as an algebraic group. Okay, so I'll say a little bit more about what I mean by an algebraic group later on, but essentially we want to think of this as, in all these cases, there's a clear group that's floating around. The group structure is there, but we also need some sort of geometry. Okay, so the geometry that we want to use here is primarily that of an algebraic variety, though occasionally we'll use something different. Okay, so this is something that's a little bit of a feature of what happens in this subject and more generally about the various geometries. And one way you can think about the various geometries that are involved in mathematics is it's a bit like various operating systems that are floating around. Okay, there are lots of different operating systems and they all do broadly the same thing, but there are subtle differences here and there. And the same is true with geometry. Okay, so in this particular example, we're going to see some of the similarities that occur. Okay, so to study the characters, what do I mean by that? And let's go through this proposition, which tells you precisely what these characters are. Okay, so firstly, let's look in the case of the n-dimensional real torus S1 to the n. So the characters, by that, I just means the homomorphisms of this group into C cross. And homomorphisms in what category? Of course, you want to preserve the group structure, but you also want to preserve the topology as well, okay? In the sense that it should be a continuous group homomorphism from S1 to the n to C cross. So the elements of this hom set, which is actually a group under pointwise multiplication, okay? The elements of this hom set they're going to be called the characters of this n-dimensional real torus, S1 to the n. And it turns out this is isomorphic to Z to the n, okay? So I'll just show the set homomorphism, but it's also quite easy to show that it's a group homomorphism here, okay? So that's version 1, if you think about the topological group structure on the n-dimensional real torus. For the second version that I want to look at the field K equals C cross, and this complex n-dimensional torus C cross to the n copies of C cross. And I want to look at the homomorphisms of this group to C cross. And the geometry, what geometry do I want to put on this? Okay, well here, this C cross is also a complex manifold. So I want to think of this as a complex Lie group, okay, so with its complex differentiation structure, okay? And in that case, if you look at one of these Lie group homomorphisms from here to here, okay, this is just also Z to the n, the same answer, okay? Finally, you can look at the more general n-dimensional algebraic torus, K cross to the n. What are the homomorphisms of this into the multiplicative group K cross as algebraic groups? And again, the answer is Z to the n. What's also nice is that these isomorphisms, even though the object on the right, they kind of look different, the isomorphism is essentially the same in the sense that it's given by the same formula. Okay, so let's see what those isomorphisms are. Okay, so on the left-hand side, we just have n tuples of integers. So an n tuple of integers, say m1 to mn. And so this should give you a homomorphism from n tuples to something inside a field. Okay, so if you have the n tuples z1 to zn, then something inside the field is you just raise each of these coordinates z1 to zn up to the corresponding power given by these integer tuples, so z1 to the z1 to the m1, z2 to the z2 to the m2, all the way down to zn to the mn, and you multiply them all together. It's quite easy to see that this function here is indeed a group homomorphism. Okay, that's just an elementary calculation, and you can check that, of course, it preserves the topology or the geometry in each case. Okay, basically because it's essentially given by a rational function. Okay, so rational functions here, if they're defined everywhere, they're both continuous, and they're also going to be analytic. Okay, so that's the reason why it also preserves the geometry. Okay, so that's a rather nice result. Okay, and one thing to note about this is that, well, the input is this torus, it's something that's continuous. Okay, but when you look at this, what's called the character groups, these three hom groups on the right hand side, okay, it turns out to be discrete objects. And this is one of the reasons why torus symmetry can be used to convert something which looks like it has a lot of continuous structure into something that you can work with discretely and use combinatorics. Okay, so let's go ahead and look at the proof of this proposition. It's rather nice, and I'll go through that slowly. So the first thing to note is that actually the most important case is to do n equals 1. Okay, let me just briefly explain why this is true, but it's a good exercise for you to show why it's true. So suppose you have s1 to the n. Okay, s1 to the n has inside it, you can pick a copy of s1 in each coordinate. Okay, and if you restrict to each of those subgroups, which are isomorphic to s1, they'll give you a homomorphism from here to here. And if we can show that n equals 1 case, so for example, if we just restrict to the case where, let's say the last coordinate can be anything inside s1, and the first few coordinates are all 1, okay, if we can restrict to that case, you'll see that that case sends z 1, 1, 1, 1, 1 down to, and then a zn at the end to zn to some power, okay? And then if you can do that for each of them, the fact that, well, this is a group homomorphism means that this tuple has to get multiplied, get sent rather to the product, okay? So that's the first thing to realize, that you can reduce to the case that n equals 1. Okay, so funnily enough, even though it's essentially the same result, the proofs in all the cases are different. Okay, so that's also something that is rather interesting about the flavor of geometry. Okay, so very often you get similar types of results. Okay, not all the time, but often they could be similar types of results. And sometimes they come with essentially the same proof, but sometimes it's quite a different proof. Okay, so in this case, it's quite a different proof. So the one that I'm not going to do is 2. And that's because it's essentially done in my video on Fourier series, okay? And the key point here is that you've got some analytic structure, you can talk about differentiation. So the key sort of tool that you use here is to use differentiation, okay? So that's what's involved there. So what I'd like to do is to prove part 1 and part 3. Okay, so that's quite kind of interesting, and you'll see how very, very different in nature the proofs are. And also just it shows you some phenomena about what happens, okay, when you change the geometry. So in the case of algebraic varieties, it's a lot more rigid what can happen once you assert that something is a morphism of varieties. Okay. So we're doing the case n equals 1. So phi here, okay, we want to pick something on the right-hand side, okay. Oh, by the way, I guess this map you can see is going to be an injective map from the left-hand side to the right-hand side. Okay, it's quite also clearly a group homomorphism. So you just have to show that everything on the right-hand side has the form something coming from the left-hand side. In other words, it has this form. Okay, so we're going to pick something on the right-hand side, n equals 1. So phi goes from S1 to C cross. That's going to be a group homomorphism, a continuous group homomorphism. And what you want to show is it's of the form coming from the left-hand side. So n equals 1 here. So basically, there's a single m here. And you show that it essentially sends a complex number with modulus 1, z to that integer. Okay, it's of the form raising z to some integer power. Okay, so for some fixed integer. Okay, so let's have a look at this and find out some facts which will show that it has to have this form. So the first thing, that 5s1, okay, this has to be firstly a subgroup of C cross, and also since S1 is compact, it's a compact subgroup of C cross. And so that means that in fact 5s1 is contained inside S1. Okay, if you have a compact subgroup of C cross, it has to be contained inside S1. Why is that? Well, suppose the image contains something which is not an S1, so it has modulus, say, either bigger or smaller than 1. So let's say it's bigger than 1. If you take powers of it, it would have bigger and bigger and bigger moduli until those powers shoot off to infinity. Similarly, if you have an element inside there which has modulus less than 1, the powers of it will get smaller and smaller and go towards 0. Okay, so it doesn't have a limit inside this C cross. Okay, so that's the first thing, that this homomorphism actually goes from S1 to S1. Okay, the image will have to be inside S1. That's the first thing to know. So we've looked at the image a little bit, okay, and we know a little bit about that. It's inside S1. The other thing that we want to do is to look at the kernel, and this will really tell you where this integer might come from. So the kernel of phi, firstly, it's going to be some subgroup, and also it's the inverse image of 1 inside here. So it's going to be a closed subgroup. So you might ask, well, what are all the closed subgroups of S1? Well, it turns out that they're quite easy to classify. Okay, so let me just kind of show you how you can classify them. Okay, so firstly, one possibility is, of course, all of S1s, but suppose it's not all of S1. Okay, then let's try to see what it might be. Okay, so, well, of course, if it's not all of S1, well, of course, it could be just 1. Okay, and that's a possibility. Just the 1 here. And another possibility is that it has some value z which is not equal to 1. So let's pick the z inside that kernel which has the smallest positive principal argument. Okay. Now maybe you say, maybe that doesn't exist. Okay, so let's just see what happens. So suppose inside this kernel phi you have these elements which go towards 1 from the top like this. Well, remember, if you have this z, you have all the powers of it as well. So if you have this with some smaller and smaller positive argument, the powers of it will cover a denser and denser subgroup of S1. So that means that, in fact, since it's a closed subgroup, you'll have all of S1. So you can find some z which has a smallest possible positive argument. Then you look at the powers of it. Okay, so you may look at z squared like this, z cubed, and you keep going around. And then you come back here and you look at the first one, which comes back to either 1 or past it. Now, if it goes past, if the one beforehand is, say, here, and if it goes past, then you'll get something of smaller argument than this original z. So it must be that the one after this one is actually just equal to 1. In other words, that this z is some primitive mth root of unity for some m. Okay, so that's a key point. So in this case, this group is actually has to be just the mth roots of unity. You can't have anything in between. Otherwise, if you had something in between, say in between this z and z squared, then looking at the quotient of this, by that you'll get some element inside the group which is smaller positive argument. So the only other possible closed subgroup of S1 that you can have is the group of mth roots of unity, which I denote with mu m. That's the set of all z complex numbers whose mth power is equal to 1. Okay. So that's nice. That tells you a lot about the kernel of phi. And note that this is really here, this is indexed by what? So m is essentially just given by some positive integer. Okay, some positive integer. So it doesn't quite line up with z. Remember, we're looking at the case n equals 1 here. Okay, but it lines up with z up to sign, and also I guess you have to watch out for the 0. Okay, so let's see what happens. So I claim that now actually you can assume that the kernel of phi equals mu m. Okay, kernel of phi equals mu m. Why is that true? Because if the kernel of phi was instead S1, what's happening? If the kernel of phi is S1, the whole of the domain, that means that everything gets mapped to 1. So everything z gets mapped to 1, and that's 1 is just z to the 0. So basically, you're just taking the 0th power of every complex number. Okay, so that case is covered. That's a possibility, and that's why where the 0 case comes to. Okay, so 0 corresponds to the case where the kernel of phi is S1. Okay, so now the kernel of phi is mu m. Okay, it's not all of S1, so you're not just mapping everything down to 1. What's phi of S1? Okay, well, it's not 1. Okay, we're assuming it's not 1 because the kernel is not all of S1. So it's more than 1, so it has some other elements. But phi of S1, because S1 is compact, okay, phi of S1, we know it's a compact subgroup. It's a compact subgroup. So in particular, it's a closed subgroup. So we saw the closed subgroups are either S1 or mu m. But it also has to be connected. So it can't be this mu m unless you have the case m equals 1, which we excluded, okay? So it must be the case that it has to be S1. Okay, so this is one of the key points, okay? So phi of S1 is equal to S1. So it's going to be a surjective map from S1 to the maximum possible image, which is S1. Okay, so that's great. We've done a lot of work to try to understand lots of features about this topological group homomorphism from S1 to C cross. It's just going to be a surjection from S1 to S1, whose kernel we can assume to be the group of mth roots of unity mu m. So let's pick a group homomorphism which looks similar to that of this form. Okay, so what's that? I'm going to let chi m denote the map from S1 to S1, which just raises z to its mth power, z to the m. And what we're going to do is we're going to compare this chi m to this phi and show how similar they are. Okay, so we're going to apply the first isomorphism theorem to both chi m and phi. Okay, so if you apply it to chi m, what do you have? So firstly, what's the kernel of this? The kernel of this, of course, is all the things that go to 1. So they are the things whose mth power is 1. That's the group of mth roots of unity. So it's picked so that they have the same kernel. Okay, so there's a homomorphism chi bar m from S1 mod this kernel, mu m, with the image. The image of this, of course, is all of S1. Similarly, phi, if you apply the first isomorphism theorem, its kernel was mu m, so S1 mod mu m is isomorphic to the image we saw is actually all of S1. Okay, and remember, what's more do we have about these isomorphisms? These isomorphisms allow you to show how the original homomorphisms factor through the quotient map. So in other words, chi m here we have from S1 to S1. Okay, factors through the quotient map S1 mod mu m by this chi m bar. That's the chi m bar. And similarly, this phi factors through the quotient map by this phi bar. So these are isomorphisms. So we want to compare this chi m to phi and show that they are more or less the same. Okay, and how do you go from one to the other? Well, these are isomorphisms. So this phi is just chi m composed with this isomorphism, chi m bar inverse phi bar. So we just need to know about isomorphisms from S1 to S1. If we can classify all of those, we can classify all these phis, or how this phi can vary from this chi m. So how much can phi vary from this chi m? Okay, that depends on what possible isomorphisms you have from S1 to S1. Right? So we're going to do that in this lemma here. Okay, so what does this lemma tell us? Any isomorphism psi from S1 to S1 of topological groups is either the identity. So if this is the identity, that means phi equals chi m. So we get the case of this phi is of indeed of this form, okay? So it raises z to this z to the m, where m is this positive integer. Or what's another possibility for an isomorphism from S1 to S1? Well, another possibility is z maps to z inverse, okay? Z maps to Z inverse, of course, that's a possibility. That's the case where you have, in Z here on the left-hand side, you have -1, okay? And this is clearly invertible. It's its own inverse, in fact, okay? So that means that that's another possibility. And the lemma states that these are only two possibilities. And I claim that this will finish the proof of part 1, the case of topological groups, because that means that we go through the two possibilities. What can phi be? Either this original chi-m, or it's chi-m composed with the inverse, which is basically, so to speak, chi minus m. If you raise to the power of m and then invert, that means that you're raising to the power of minus m. So that's how you get all the negative numbers like that. Okay, so we're reduced to proving this lemma to finish off the case of topological groups. Let's do that now. Okay, so why is this true? So the first thing is that here's our S1, okay, and it's got a 1, and it's got a unique square root of 1, which is not equal to 1, which is -1. So since psi is an isomorphism, it has to fix 1 and -1. And psi is a continuous map, so it has to preserve the connected components of this S1 minus these 1 and -1, which is mu2, okay, the square roots of 1. Okay, so it has to permute these two connected components of S1 minus mu2. Okay, so either it fixes the upper semicircle and the lower semicircle, or it swaps the upper semicircle with the lower semicircle. Okay, they're the only two possibilities. So the identity fixes both of them, and Z maps to Z inverse, of course, swaps them. So if we compose psi with Z maps to Z inverse, then we can assume that it actually preserves, okay, the upper semicircle and preserves the lower semicircle, okay? And the question is, what does it actually do on the upper semicircle, and what does it actually do on the lower semicircle? So we want to show that, okay, since we can compose with this, actually we want to show now that this has to be the identity, okay? So let's just see how it is the identity, okay? So the way we're going to do it is as follows. It's a continuous map. So if you can show that it's the identity, this psi is the identity on a dense subset of S1, then you show that it is indeed the identity. And let's do that right now. Okay, so we'll do it bit by bit. So I'm going to look at I. What does psi do to the I? Well, I is a square root of -1. There are two square roots of -1, I or minus I. So since psi maps -1 to -1, okay, it has to map 1 to 1. It's an isomorphism, so it has to map this -1, the only non-identity square root of 1 to itself, okay. So I has to map, psi has to map I to one of the square roots of -1, so it's either I or minus I. But psi also preserves the upper semicircle, so this has to be preserved. So that means that this is actually equal to psi of I, okay. So since it preserves that, okay, so essentially the psi has to preserve square roots, but what do I mean by that? So for example, if I take the square root of this I, now I'm over here, okay, this has to get mapped to one of the square roots of I. So that's either this one or this one. But of course, this one is in the other semicircle, so it has to fix this point here. And if psi fixes this point, it fixes all the powers as well. So it fixes the square, its cube, this one, and so forth. And then it also has to fix the square root by the same argument of this psi has to fix the square root of this, which is this one here. And when you keep doing the square root, you'll find that the group that they generate is a denser and denser subgroup of this S1, and eventually you do actually get a dense subgroup of S1 that you know is fixed by psi. And that completes the proof of this proposition in case 1 of topological groups. Okay, so that's rather nice, and you can see it's quite an intricate argument that uses a lot of topology, and that's because that's the geometry that we've chosen in this case. Okay, so let's switch gears now and move to part 3. We're looking here also at the case n equals 1, and we want to show that the algebraic group homomorphisms from K cross to K cross is isomorphic to Z. And by the same reasoning, okay, we just have to show that every homomorphism from K cross to K cross, which is of algebraic groups, comes from this map where n equals 1. Okay, so we're going to pick some such homomorphism phi from K cross to K cross. And it's going to be a group homomorphism. And it's also going to be in the geometry of algebraic variety. So let me say a little bit about that. So the key point is that we look at the coordinate ring of K cross. So K cross, what is that? It's basically the affine line A1x where you removed 0. And so you want to look at essentially rational functions on this. What are the rational functions on here? Okay. Well, if you want to have a rational function that's defined everywhere except possibly at 0, the only things you can have in the denominator are powers of x. So this is basically this Laurent polynomial ring kx x inverse. That's the coordinate ring. And so the important thing here is that you can pull back regular functions to regular functions. So there's a phi star map, which is a map of k algebras from kx x inverse, this coordinate ring. Okay, so that's a function on this one-dimensional torus, to a function on the one-dimensional torus kx x inverse, a k-algebra homomorphism. Okay, so we're going to use this fact. So we're just working with the geometry at the moment. Okay, we have this phi upper star k-algebra homomorphism from here to here. Now, of course, to work out what this is, it has to fix k. So you just have to say where x goes, and that will tell you what that is. Okay, so what's x? So phi upper star x is equal to what? It's inside here, but x is a unit inside here because the inverse, x inverse is inside here. Okay, so that means it has to be a unit inside here, but there aren't that many units inside here, or rather, you can classify them quite easily. Okay, they're essentially, well, you can get non-zero elements inside k. You can also get powers of x, and basically you just get products of these things. Okay, so alpha x to the n. Those are the possibilities for you, what you can get, alpha x to the n. Okay, so that limits a lot what this map can be. This phi upper star will kind of tell you what that is, okay? Now, what we're going to use, we haven't used the fact that this is a group homomorphism. In fact, funnily enough, we're not going to use the whole force that it's a group homomorphism. We're just going to use the fact that it preserves 1. So this is something about the rigidity of algebraic morphisms, okay? Phi upper star of 1 is equal to 1. This is a k-algebra homomorphism, okay? So what happens there, okay? So that will happen, or rather, the more precise thing I want to say, this is not the reason, so maybe I'll just erase that. The other thing that you need to know is the fact that it preserves 1. Okay, so that means that when you plug in 1, okay, you should get the same answer. At the value 1, okay, what is phi upper star x? Okay, so at the value x equals 1, you get alpha. So that implies that alpha has to equal 1. Okay, so you're thinking about this phi upper star. If you pick this to be your phi upper star, where does it send 1? There's a corresponding map here. Okay, and the answer is that it's going to send it to alpha. Okay, and so since 1 gets mapped to 1, you need alpha equal to 1. So basically, this phi has to be x goes to x to the n. Alpha equals 1, so it has to be x goes to x to the n. And that completes the proof of part 3. Okay, so now we have it. We've proved this proposition, which really tells you what the character groups of tori are. And we've done it in 3 settings: the topological setting of n-dimensional real tori, the setting of complex tori, and also the setting of algebraic tori. And the answer is the same. It's this set to the n, okay, where n is the dimension. And that is a discrete set. And this allows you, in many cases, to reduce problems where there's a lot of torus symmetry to a combinatorial analysis involving z to the n. I hope you enjoyed this adventure in pure mathematics.